today's lecture is going to be about 2D filter. It's an extension to the previous lecture on the 1D case. We're gonna take you through how we could compute sliding windows, cross correlation, and convolution. And we're going to look at a couple algorithms, in particular dilation and erosion. And we're going to look at smoothing, mean filter, Gaussian filter. We'll see Lapacian filter. All right. So first, let's talk about sliding window in the 2D case. We already looked at in the 1D case. In the 1D case, the window kind of looked like this in the 1D case, but in 2D, the window is a 2D as well. So in this case, suppose we have a filter size 2 by 2. So the first window is going to be in the row wise 0, 1, 0, 1. So I have 0, 1, 0, 1 here. And the second window will slide to the right. And over here, so let's just erase this so you can see this number. So the second window, if we turn it into the column format, so we have this image to column representation that as I explained in the previous lecture, that reason is that instead of sliding the window implementing as a for loop, that's the most naive and intuitive way to do, but it's not as efficient in terms of computation. So we would like to turn into a column format. So in this case, 1011, 1011 for this column, and then next window, and then we have to go to the next level. And we can pay attention to our stride size. So for stride size equals 1, meaning that when we shift to the second row of these windows, I would like to just go down by 1 position. So this is my 1, 2, 3, 4, fifth window. 1, 2, 3, 4, fifth window here is 0, 1, 0, 1. And we can continue this process for the rest of the location. In every single location, we have draw 1 window like this. So this is just, I'm doing this repetition just to as a practice of trying to internalize how the window sliding really works in the 2D space. And at the end, we get this column representation. You have seen this in the 1D case in the previous lecture. And so now I'd like to go through one of the interesting algorithm we could perform on a 2D image, and let's start with a binary image for dilation. So the idea of dilation is that we have an input image look like this, 1 and 0, and want to dilate them, meaning that for every bright pixel is 1, we like it to kind of dilate into its neighborhood. So if we do a 3 by 3 neighborhood, kind of go like this, but where I want to start with the easy example, which is only going to the 2 by 2 window neighborhood, want that to dilate in this location. This is what I wish to accomplish. There's another one in the corner, so dilate in this location. And so the first is that in order to convert into the image column, we would like to preserve the shape of the input. If I run a 2D, we actually have a boundary condition here. In the previous case, we just kind of ignore it because so we have a fewer windows. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I think we have the boundary location 16. But here, all the 0 actually come from this kind of empty space. I did not define them, what they are. But in this case, I'd like to specifically add this. So suppose I want to add it to 0, 0, 0, 0. In this case, I pad them so that there will be the value I can read them. And so then we convert into the column in the next step. So we can still have 16 locations. And then, so for the erosion, for actually dilation, so one of the filters we want to run, this window is actually this max. Basically, if I consider, say, with his location, I want to find the maximum in the neighborhood. We happen to have 1, so I'll fill 1 myself. So if you look at this location, look at the neighborhood. If you happen to have 1 maximum, so I will fill 1 myself as well. So this is a way that we can dilate into, make 1 pixel and kind of dilate to the neighborhood pixel. So we can see we apply this max operator by column. For each column, I want to apply the max operator. So it's basically to find the max value. So it's a little bit like a max pool in this case, in fact, is exactly what it is, a max pool. So do a max pool down the row. I'm looking very quickly. So that's pretty simple. As long as I see the one, I just put one. And then when I would like to convert this back to the 2D representation. We can use wrap row. So wrap row with the 4 as my width. So we're going to wrap them around 1, 1, 0, 0. And second is 1, 1, 0, 0, which is my second row here. And third is, let's draw some boundary. So 0, 0, 1, 1. And I have 0, 0, 1, 1. You can see that this is the result of dilation. Let me erase some of this so I can see the effect. So one kind of, it indeed, let me use a different color, kind of indeed dilate into its neighbor. And so after applying this max pool to the columns representation of your image. Okay, and so erosion is another operation. We call it formological operation to the binary image. Is we like to do a bit more like a reverse process. So this 2 by 2, let's just say consider 2 by 2 neighborhood because they're all one. They would like to erode them so into just one of them. Okay, so at least 2 by 2 will keep one. But then if you are smaller like this, it's gonna disappear. So that's what we like to accomplish as an effect. So we want to have just only this one left. Everyone else will disappear as erosion. So in this case, we like to start by padding. In this case, I would like to pad not, in previous case, I pad with 0. And in this case, in terms of in erosion, I actually want to pay with 1. You can see why I want to pay with 1 for the case of erosion later. So, and then we convert them into, actually, I convert them into this column format. And in this case, then I can apply a pool. This case, instead of a max pool, I would like to apply to the mean pool. So the idea is that if you have 0, anywhere in your neighborhood, you will just cross that pixel out. So here, 0, 0, 0, 0, 0. This is 1. Everything is 1. So this actually correspond to this particular window. That's why we want to save. So this is any only one that can survive after erosion because they are 2 by 2. And then 0, 0, 0, 0, 0, 0, 0, 0 down here, except for the last position, have 1 here. So it turns out because I padded with 1, sometimes I might not want to just remove the boundary pixel here. So in this case, if I padded 1, I want this to be preserved for this particular erosion process. And then after the last step, I'm going to this is 0. Going to wrap them back to this 2D representation, 2D map. 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, and 0, 0, 0, 1. So that's the result of my erosion operation in this block, in this section. Okay, so since to highlight, we will pad with 1. And then we run the pooling operation using minimum, and rather than maximum. And the idea is that if for every window location, if you have a 0, you have any 0, it means that it's not big enough for you to keep. You only keep when you have 1, the filling up entire window. So you can imagine that you could increase this filter size to 2 to 3 to 4, have different sort of effect. In the next tab, we're going to look at in the 3 by 3 case, and by writing Excel functions. And then this is that we could also apply a correlation to 2D images using similar philosophy, that we take 2D image and turn into this presentation. If we only focus on this part, you might have seen this pattern before. So this is a pattern we saw in the 1D case. If you don't look at any other places, they just correlation worked in the same way in the 2D case. In that we have a window, then we have this filter over here, H. We have a window that like this in the matrix form, and then when we just match them, 1, 1, another 1, and it's 4 different location. And then we do a like dot product to get this value. That's what we want. And just calculate this one. But before that, I will just practice one more time. Maybe this time for image pad, I'm going to do copy the neighbor. So in this case, I'm going to do 1165. This is going to be 0235. So the reason of copying the neighbor to pad them is that so that I don't have that discontinuity. Or if we have a 6 drop to 0 that's introduced some kind of artifact, we want to avoid that. We can copy this, and then we have finished this. And also the reason we pad them for a 2x2 window is that we would like to preserve the shape when we wrap them back. So there's only way we can wrap them back to 4x4 image later by padding them. So we have enough window at the last location in the image. Okay, now having established this, let's just see, this is second window. What is my second window? First window is here. And second window is here. Second window going to come down here is 2040. What if I just erase all this so that I don't no longer use this one? Okay, and then this is my third window. Fourth window is actually this boundary here. So this is here. So 1, 1, 1, 1, I think. And then we can skip to the next one. And my strike is 1. So I will do this one. Next one is 3421. It's down here. And next one is 4014. It's 4014 down here. And now we can actually apply a filter to it. So, and in the 2D case, even filter is actually in the 2D as well. So I have 2x2 filter. But to compute correlation, cross correlation, using this matrix format, column matrix format, we just flatten them. So into flatten this 2x2 filter to 2, 1, 1, minus 1. And then we can do the dot product here. So this dot product is 2, 2, 2, 4, and 4, right? 4, let's just use the color to guide it. So this and this. So this going to be 4 plus 4, which is 8. This 8. Is that right? I think so. And this is easy, 1, 1, 1, 1, and 2, 1, 1, minus 1. So it's going to be added this all up together, 2 plus 1, 2, maybe write out plus 1 plus 1 minus 1, which is 3. And last one is going to be 8 because 2 times 4, 8 plus 0 plus 1 minus 4. Okay, so it's going to be 5, right? And then after do that for every location we're wrapping around. So this step is pretty easy. So going to be 3, 8, 0, 3, 11, 5, minus 1, 5, 3, 5, 12, 16, and 0, 6, 9, 15. Okay, so like you can see here, the only thing that's added new to the 2D case from the 1D case is this extra step of input this image to column step, image to column presentation step. Then with some padding if you want to preserve the shape, and also this flatten stage to take your 2D filter into this 1D form, and then you can apply the same cross correlation by a large metric multiplication they can put on the GPU. Instead of on CPU, you have to write a for loop to go down there very slow. Okay, and for convolution, and if as in the 1D case, the convolution, so this step is going to be the same, that we will still want to they just do the image column and do the padding here. So I'm going to repeat this process very quick with copy as my padding mechanism. And this is going to be 0, 2, 3, 5, and 5. And then image column, this is going to be my second window. It's over here. So 2040. My fourth window is going to be not here, but down here. It's just like this, maybe prettier this way. It's going to be 3, 4, 2, 1, and my final window. No, 1, 2. Okay, I make a mistake. This is not the right one. My fourth window is actually here because I padded it, so I could have get my fourth window over here as 1, 1, 1, 1, which is the same as before. 3, 4. I realized this is exactly the same as the previous case. which is on purpose, 4014. Okay, and so then I have this filter which is the same, but in order to compute convolution, it turns out to compute convolution, all you have to do is flip this filter into but along x and also along y. So as a result, if I flip them along x, it's going to be 1, 2, and -1. You can see this 2 and 1 flip, 1 and -1 flip. And then I flip 1 one more time. So instead of 2, 1, I get 1, 2 over here. So for this one, I flip them again. There's going to be, what is it? -1, 1. So just to be careful that what I just did is not transpose, it's actually flipping x and y both in order to get the flipped version of this filter. Once we have a flipped version, then this process is the same, going to be flipping it. And that's going to give me, and then we'll do a metric, this times m, suppose this is m, which is still the same, metric multiplication between the flipped version of h, they'll give us the convolution. And so, and then we can calculate this. It's going to be -2 plus 4 is 2. And this is going to be 1, 1, 1, 1 to be -1 plus 1 plus 1 plus 2 is going to be 3. And that one is going to be -4 and plus 0 plus 1 plus 8 is going to be 5. Okay. So, and at the end, we're going to wrap them and 5, 5, 17, 14, 5, 5, 17, 14, and 3, 11, 15, 13, and that's lastly 6, 9, 15, 15. Okay, so that just completed a convolution, which is very similar again to cross correlation, except that you flip the filter and you can calculate this. And that's also the central part of the multiplication between your flatten filter and also the color representation of the total image is based on allow you to perform that sliding window cross correlation with this one massive metric multiplication. So the mean filter, we talked about it in the 1D as well. In 1D case, mean filter is going to have an effect of smoothing things out. So when smooth this image, so 4, 5, 3, 4, what if we can just like take the average of this window and just replace 4 with the average, basically kind of 4 distribute some more pixel value into some neighborhood. So it looks, as a result, look kind of smooth. And then we look at the 2D space for the smooth, the filter is going to be, since we have 4 by 2 by 2 is 4 locations. So if we just take a 1/4, a quarter from each location, and then sum them up, and then we flatten them. So this is our mean filter. Take a mean in each window, and then we take the maximum location, which will get the same result. So it's going to be, in this case, is going to be, what is this? 5 plus 4 plus 3 is basically 12 over 4, because 5 times power 4 plus 3 equals 12. And this is going to be 4 over 4 equals 1. So the 3 over here, 12 over 4. So they're going to be 4 plus 3 plus 1 plus 4 over 4 is going to be 7, 8, 12 over 4 is 3. So there's a result. And then at the end, we again wrap them back to the image. We'll see that a lot in today, kind of the process of sliding, turn that into image to column and then back to image many times. This, and we'll see even more when we get to convolutional neural network. We'll see the similar process in play as well. So you can, now we're trying to establish that you'll become familiar with this process before you even get to deep learning. And that's my intention of taking our time to go through the 1D filtering case and to 2D filtering case now. Okay, so now we complete some of the simpler cases to help establish intuition. Now I'm gonna do a lot faster in the Excel tab to code something up very quickly as fast, and while you can follow it. And this is going to be your activity as well. You can follow as much as you can, and once we have recording, you can also pause them and follow it. Okay, now we're gonna do the sliding window. And so for this one, again, the first window is here, okay? and not about this not correct because I have to turn it into a column form. So use two column. Okay, and then I can copy over here. I can copy how many can I copy? If I copy is actually out of bounds, so this when I have to wrap around. This case I have not introduce padding yet, but just with no padding, so I have to wrap this around. Once I wrap it around, I can copy over here. I think since F2 can see you can see the visualization of where we are. But if I copy one more time again, you feel like okay, actually off this one is out of bound. I'll use my mouse to drag to another row. This is still okay, but if I copy one more time, now it's all out of bound. Then we can drag to the last row. I think we can now without padding, we can no longer slide outside of bound. So that's all we get. Okay. I have built this function for you to perform this. So just do image to column. This is a MATLAB function as well. MATLAB has something similar, but I built this myself. So going to be like this. I select the window and then I want to select the filter size as 2 and 6 and then and try is 1. I have this I just start with a parameterized version. And so this is 2 and 1 filter size and try. In this case, you can see we get exactly the same result as we just do it by hand one by one. And then we can try this. If I do filter size equals 3, you can see that each window gets columns longer because we need 9 elements per column, but also fewer columns now. We have then as a result gonna fewer pixels unless we should pack them later. Okay, so this is what go back here. Let's do a 3 by 3 filter case here. So we have this. You can see that this is similarly, I have already do this. And but I can implement using image to column, and I have filter size 3, and then let's try 1. Okay, didn't okay, comma, and let's try 1. Okay, let's redo this. Image column, I should select this image first. First argument is image array. Second argument is filter size. And third argument is the stride. So I just select them. Okay, now I have this image column. And let's just do image column one more time. Image to column. And I go up to select my input image here. But in this case, I would like to try a different stride. So you can see the effect of stride. So we're going to do filter size still 3 and then stride size 2. Stride is that how many location you will take you will move the window before you take another one. So for instance, this is 3 by 3. My first one is here. When stride 2 means that the next window is over here. So then you can see that if I just going to do a stride 2 down here, so we can at most have in 4 before sliding the window out of the image boundary, and then that matches the result of image to column given a stride size of 2. Now we can use this to implement dilation and using functions. So first, for dilation, the goal is that we want to have this input image, and I would like this to dilate into this way, kind of like this. But when this is going to be a 3 by 3 case, so my goal to be something like this will look like this. I think I want this go like this. We'll see whether it works that way. Okay. And then so first, because I would like to get the image back, I know my 3 by 3, we're going to go over by 2. So I want to pad this. So I actually have an image padding function also I implemented. It doesn't come with Excel. So image pad, I want to pad this image with, what is it? Pad width is 1. So I actually have parameters set out here. And pad value, I want padding with this value 0 for now. Okay. So like this. All right. So the next is that with the padded image, I could convert into the column format. And that will be able to perform a lot of this pooling operation in this format. So I could do an image, not here, here, image to column. I select this, my padded version image, And I could use a palm sign. Palm sign allow me to select whole array because we use dynamic array formula here. And then the filter size is 3. I can select my parameter here. And strike size is 1 over here. And then voila, I get the column representation. And then for dilation, the operator is max. I want to run max pool over it. So what I want to do is do max, okay, and then select all this, and then I can copy them over. But today I want to introduce you the function that's actually building into Excel called by column. This is getting to the functional programming. So if you use by column, I'll be able to select this whole array of the column representation because I say use palm sign. You can see that the entire array being selected. And then I will just give the function max as a parameter in second argument. And you will apply max in every single column and get this. Okay? So functional programming right here using by column. And once I have that, the last step is wrap them back into my image. And there's going to be wrap row. Okay, and select my image using the palm sign to select the whole array. In this case, the row width is 8. So I type 8. Ta-da! No, it didn't work. Why? Wrap row. What does it say? What is the error? Invalid name error. Red rules, is that right? Okay, I misspelled. This is red rules. This is okay. This is misleading. It's actually red rules. Okay, now I have this one. So does it seems like what we wanted, similar to this padding? So you compare the before and after. So then another thing I like to do is I could maybe you select this row, but I add Control 9 is a way I can hide it. I think Control 9 can see the result after easier. So it's kind of spreading. It does looks like what I wanted to accomplish, right? Dilation. Okay. So now I just select this and do Shift Control 9. I'll be able to unhide this and turn them back into where what the whole algorithm can see. And so for erosion, so the process is pretty similar. So except that so instead of padding value to be 0, I'm gonna pad with 1. I just type 1 here later. So now first is padding. Also, it already explained why we need to pad. So I pad this image by 1. Okay, I just type it in. Hardcode 1, 1. We'll get the same result. Pad is 1 because I'm gonna run erosion. I like the border to be 1. And I do image to column. And I select this padded image here. I use palm sign to select the whole thing. And filter size is 3 and 1. This hardcode enough because it's faster. Okay, and then lastly, well, now we could do the by column and also select this array and with palm sign. But notice that we're gonna do a mean instead of max. Mean pool to give us the effect of erosion. So what does erosion mean? Let's go back a little bit. So this is going to be erode out. This only thing that survives here because it has a full neighbor of 1. So that's what I would like to accomplish. And for this, maybe give this benefit of doubt. What if the boundary is as 1? So I want this to survive as well. So these are two things I would like this to survive in this example. Okay, so that we do this by column. Let's see that we do now wrap the rows, wrap them back to wrap rows here. No, one more time. Wrap rows. And then select this and palm sign, select entire row and by 8. Okay, ta-da! So I did get this 2-point left. Does it match what I wanted to accomplish earlier? So let's see. Let's just select this in the middle, in the intermediate layer, and hide it, Control 9 temporarily, so we can just play with this. Okay, so you can see that this eroded back to only 1 pixel, and then we can just in real time you can see the effect. I just can add in more. It's still not surviving. Okay, not surviving, but as soon as I add this one, bang, you have a new pixel here. Now, as soon as we remove this, some neighborhood back to where we are, put 0 in, so we can see the effect. Okay. Okay, so the next 2 more operations I'm gonna talk about, open and close, which is by combining erosion and dilation in some interesting way, you can accomplish the effects. For open is that I have these 2 kind of connected with something really thin here. I want this to disappear, to open this up. So open this up because it's not thick enough. Open this up. So there's a good for removing some kind of small artifact in between them, but there should be two components if you want to accomplish opening up into two components. So the first step is erosion. So erosion, so for open is accomplished by erode. Let me just write it down a little bit. And dilate. And then there's an opposite of this, close, which is in opposite direction as well. Dilate first and erode. So there's a good review of what we just did with erosion. So erosion, first step, again, I want the path for erosion. So I would like this to be actually 1. Pad with 1, I think. If not, I'm gonna fix it. So image pad, select my image, and then pad with 1. Actually pad with 2. Wait, 2 or 1, yeah. 1, because I want to have a 1 border 1 like here in the boundary, because my window size is 3 later on. And then go back here and my pad width 1 here. Okay, so that's what I have. And then this image to column, select my pad image here, palm sign, and filter size, and try 1, fill this whole thing up. And then this is going to be mean. I wrote it down for, and it's going to be by column. Select this whole column, and then actually palm and mean. Okay, so now, and at the end, very quickly, I just reproduce red row, go back up, select this, come back down. Actually, no, just 8. Okay, now have you just eroded. Now you can see this. Okay, we actually erode back here. So now my little tiny link is being gone, but it's become too small. How can you restore back to the 2 component? We want this 2 component. So you can see, oh, maybe I just dilate afterward. That's exactly what we should do. So to dilate this image pad this, and then with 1, also with 0. Now dilation want to pay with 0, which is opposite. So the pad value is actually 0 here. Okay. And then image column, image to column. This is, we're gonna, as I said earlier, we're gonna do a lot of image to column today. Filter size and try 1, get this column representation, and then we do this efficient by column kind of tensor operation. And then this is max, okay, opposite. So I actually wrote down here to remind myself for dilation is max. And then when wrap this around, it's now wrap rows, and select my image, and palm sign, and by 8, da you can see that the links is actually disappear. If you don't believe me, I can scroll all the way back up to right before my input image here. Where is my input image? Here is my input image. I select this range of rows and I hide them so I can see them just right next to each other here. And I can kind of play with it. So see, if I add a bit more length, because my 3x3 window is not gonna have no effect. But the moment I add this one, they are actually connected again. So this 3 thickness of 3H is not being removed by a 3x3 open operator. But as soon as I move one of them, and then you can see the effect of being removing this link, open it up as 2 components. Actually, now it's not essentially like this one, like this way, right? You get this link between the 2 components removed. So now I'm going to restore this by select this 2 and then Control Shift 9 to open this up. Now I'm going to do something, repeat this process one more time. So I like repetition because we could really hammer in the concept here. So for close, as I said earlier, the process is dilate first and then erode. And the goal is to close this. There's a little gap here. I want to close this. You can imagine that if I dilate this, and then we erode again, so I actually can get this back, okay? This is the goal, to link this. Okay, let's see where I can do this. So we're gonna pad this picture with 1 and pad value for dilation. Padding is, what is it? Pad with 0. Wait. Actually, one more time. Image pad. I want to select this input image. So and then I want to pad with 1 width around it, and then value with dilation, the value I want this to be 0. Okay? Yeah, I can very hard for remember. Let's just check. It had to be opposite. So dilation is earlier. Dilation paired with 0. That's true. Yeah, that's exactly what I want. Dilation paired with 0, and then this is going to be pretty mechanical now. Image to column. Select this image, and then just fill the size and try 1. Enter. Okay, scroll down, coming down here by column. Right now, it's select this, and then max. Now this should achieve the and effect of okay, 8. So now should be see this dilated. The image is actually dilated. You can see that this we have this kind of dilated. Now they're connected together, but it looks too fat now. We just have to reroll them back. In this case, I'll just do a pad again, select this image, and then pad with 1 with value 0. Actually, for erode, I want to have 1. It's opposite. And then we do image to column. Let's do slowly so I can do it correctly. Okay. And then select my image and palm sign. And then filter size and straight 1. Filter 3. Filter size 3. Straight 1. And then do a by column. Column. And then select this array. Palm. And then what is it? Min or max? It's min. And then now I'll do the final, turn it back into my 2D format. So it will be red rows, palm, rep count 8. Okay, ta-da! Now we can compare this output with input by hiding the layer in between, so we can easily visualize Control 9. Now you can see the upside down. Okay, you can see that this thing being connected. And this is even connected with edge as well. So what if I make the gap bigger? So all of a sudden that no longer connected. But as long as the gap is smaller than the size of the filter, you can actually get connected effect. Okay, so it's pretty fun for you to play with. When you actually implement it, you can play with it. It's pretty rewarding. I might find myself once you can play with it. Control Shift 9 to open this. Okay, all right, so now we can finally get to the next stop that we looked at dilation and erosion and open and close. You realize we're not introducing any filter values yet. So that's when we actually want to introduce my filter, supposed to have a min filter. How does it work? A min filter, we actually looked at the min filter already. So let's make it implement a bigger one. So now the first is we'll have a image now is bigger, 8 by 8. And then first, I would like to pad it. I want to eventually run a 3 by 3 filter. So I need let's pad this image in my input image to be, and then pad width is 1, pad value is 1. Okay, so I have now padded one. So now I can run the 3 by 3 filter without losing a pixel location. So we're going to do here image to column. This is process exactly the same as earlier binary images. So and then 3.1. So I have this column version. Now I can finally run my convolution. So for me, I would like to have 1, 1, 1, 1, 1 over, but I want it to be summed to 0. I mean summed to 1. So one way is that I can just overnight. Select the whole thing overnight. So that's my min filter. And first step, convert my filter from 2D to 1D so I can do this correlation, cross correlation as a matrix modification. And that 2 column is actually, I do 2 many 2 column, but here actually I want to 2 row. So I can 2 row, that's what I want. And I could do the matrix modification between them, matrix modification between this and this. I'm gonna select this. I can use the palm sign. So like a whole thing, ta-da! So I have this the result of applying the min filter as if you are sliding the window every single location, compute the cross correlation with the window across. Instead of iteration, again, emphasis, instead of iteration with for loop, you use parallel matching multiplication by first convert them into this column format. And once you have that, let me just show you if I wrap them back to A by A picture, then we get a smoother version of the apple. You can kind of hardly tell it's apple because it's smoothed out by the mean filter. So let me just again select the things in between so you can see them side by side. If for the effect, they just Control-9 to hide them. And move out a little bit, you can see that side by side now. So I can change my image ID to the 1, so I have this dinosaur, kind of smoother version of the dinosaur. Okay, so and the key. Okay, so that's how smoothing work for a mean filter. And a mean filter is not the only thing that could. We can also apply a Gaussian filter to accomplish it. Let's just open it out one more time. So for a Gaussian filter, instead of 1, we suppose we want to have a bit more weight to the center and a bit less weight to the side. And to the discrete version of Gaussian can be approximate with, if we have a 3 by 3 filter, there's a ways you could approximate that, but today we're not gonna parameterize it. I just give one Gaussian filter value now in our example. So one example would be this roughly put 4 in the middle. Maybe I would like to basically half of what is in the center, and then another half of what in the center. Basically, the further you move away, it kind of exponentially decay. But I still like this O to be kind of add out to 1. So since we have 9 locations, I'm gonna divide it by 9. And then if I 2-row, turn the 2D into 1D, a row vector. And then with that, I could just do a metric modification, select the entire thing with a palm, and I gotta move out a little bit to select my column representation. So this is the same representation we can use right here. I select this one and with a palm sign and close. Okay, now I get this. So this is, and then I wrap them back to the 2D with 8. Okay, ta-da! So I just finished computing the Gaussian filter at every single location. The result is like smoother, but it's a bit more preserving the fine detail at where you are because you have this exponential decay of your filter, but still as achieving the smoothing. And so you can compare this. This is the key. You can kind of tell. Let's just maybe do one more time. Just close all this in between, hide all the in between, so we could see the effect of applying Gaussian filter. Control-9. The key, smooth version of key, and go back to the dinosaur, go back to the apple, so you can see the result of smoothing. Okay, now I'm gonna unhide this with Control-Shift-9. Going to look at the next example of Lapacian filter. We talk about Laplacian filtering in the 1D case, and so it's for detecting changes in the image, like edges and boundary and so on. So Laplacian filter, before we even apply this, why don't we just turn it into this column format, and then the whole thing was just very similar to 1D case. So this let's just peg with, maybe peg with 0 for my side here. So this is my apple with 0 in the boundary. And then I just do an image to column, and go back out to select my image with palm and filter size 1, strike 1. Filter size 3, strike 1. Get my column representation. So this Laplacian filter in 2D can be approximated kind of like this. You can see that with negative in the middle, but a little bit positive to the side. And this is with the second derivative. So the proof, you can see that it can capture the maximum of the changes in the direction. But before I kind of use this, I can use it as is because add that to 1, like you can see. And so I could just but before I use it, still I have to convert into a right 1D shape. I convert into 2 column, and 2 row. And then I could do matrix modification between the two. Select this, select my flatten filter, and then select my columns representation, and then we can get the result of applying Laplacian at every image location. And the last step is the same. By wrap them back into 2D, you can actually see it. I'm gonna wrap them back into 8. You can see that, okay, this is you can see a little bit the signal kind of around the border of this apple, okay? And then just come pull them back to hide the rows in between, and Control 9. All right, you can see this signal here, and then we change. You can see the kind of catching the boundary of the shape, okay. And then at the end, we usually add another extra step to say threshold. So to compute threshold, I will select my image and just greater than my threshold number here, 200. So we can wait. Doesn't quite work. Okay, actually it does work, but it's because it's true and false. I hope they're showing 1 and 0, but not. So I actually have to produce use if and to say, okay, output 1 if over the threshold, output 0 if not, and then to get this binary mask kind of at the high responses above 200, then can mark the kind of ages of my dinosaur. If I do 2, is apple. You can see a little bit kind of around this edge of the round, a circle of the apple. So this show that this effect of Lapacian filter. Again, you should appreciate that by doing this metric form, we could do that in parallel very quickly. And once we get to neural network next week, you can see a tons of those metric multiplication format like this. For Sobel filter, the idea is, again, another way to detect edges by considering the gradient and magnitude. We talk about the concept of gradient and magnitude in the feature lecture. So kind of repeat this same process. Paired with 0, then paired with 0, padded it, and then image to column. We've done this like many times by the end of the lecture, I think. And now this is interesting because I want to pick up the gradient in X direction. And so this is a spatial filter designed to do just that. And so equals the 2 rows of this particular filter. And then once you have that, to apply this filter at every single location is, and then just use palm sign, it's convenient to select entire array and this array, and then let's wrap row around, red rows, and then this one, palm sign with 8, You can see that this catching us on kind of these vertical edges, and this is picture not a clear, but if I change to 3, maybe the key, you can see that there's vertical responses. And for horizontal weight, both are GX. It's one of the GY. Okay, this is GY. And so then, and this is a rotative version of this. So I will go into 2 row of this filter. It was handcrafted to pick out this signal. And in the convolutional neural network case, you're going to see that we would like the network to actually learn this filter pattern rather than we handcrafted it. And it turns out to be much more powerful. Okay, now match application. Okay, I selected the wrong one. I actually want to select the column representation, not this one. Go to the column representation here and pound sign, enter. So there's a result. And then I'll do is red rows and this pound dollar actually 8. Okay, so now you can see pick out the pattern in another location. And then when I compute magnitude, it's going to be like this square root of gx squared plus gy squared. And that could be implemented as this. I select gx, which is here, palm sign, and square by, okay. And then go back down here, plus select this palm sign, so the whole thing, and this square. And so this is my equation. And then we get the magnitude. You can now kind of see the edges are being that has a good responses. At the end, we do another if statement. If this is greater than my threshold, and then I'll do 1, otherwise 0, and then we get to this. This is my shape. Okay. And then if you say we can lower this ratio, it can include more. If I raise this ratio, it can include less. So there's a phenomenon. It's too high, I have nothing. Okay. All right. That's all I would like to cover for the filter 2D. Thank you for listening.